Hello, good afternoon. You should, you hear me and see the desktop? Everything seem okay?
Yes,
Yep,
Professor.
okay, great. Okay. Excuse me. Okay, so last Wednesday we went over the homework assignment. The homework assignment is up there now. It was up there later that Wednesday evening. Okay, so the homework assignment is up there. This will be your last program assignment. Excuse me. We're getting pretty close to the end of the semester. After this week, there's 2 more weeks of classes left. There's 2 more weeks of classes and then final exams. So there's only 3 weeks or so left this semester. So this will be the last homework assignment. Okay, so, and it uses up everything we've learned up to language 7. It doesn't include anything about language 8, but it really gets across everything in language 7, because you really have to digest the interpreter to be able to to repurpose the interpreter into a syntactic analyzer, which is basically what you're doing. You're gonna reuse chunks of the interpreter as the analyzer. Then you have to redo some of the things the interpreter does, because the analyzer does them in a different order. So you have to really understand the interpreter to write the analyzer. Okay, I think actually almost literally all the code you need for the analyzer is in the interpreter. Pretty close to all of it is there in the interpreter, but you have to kind of see how to repurpose it. Change the order, maybe make some subtle changes to it. But the vast majority of the code you need for the analyzer is in the interpreter. Okay, so what we'll do is today we're going to go back to language 8, but maybe next week we'll go back to this and see if anyone's got any homework questions about it. So instead of talking about it more today, we'll wait a little while and then we'll go back to it like maybe a week from today and see if there's any questions that come up about this assignment, because it's pretty challenging in the sense that you don't write you will end up writing a program that's hundreds of lines of code, but most of those lines of code will come out of somewhere from the interpreter. Okay, so yeah. Oh, I'm sorry. Just real quick. This is the interpreter, but it's been stripped down. In here, the interpreter has almost all its runtime checks removed. So you have to go back to the language 7 interpreter to see what all the checks were. And then you're going to end up putting them into this file. Like right now, this file is almost empty. I wrote a little bit for you, and then it's got all these empty methods that you have to do that do var, set, print, Boolean expressions. So this is where and you don't just go to the interpreter and copy what was then from there and here, but you're pretty close. It's pretty close. What was in. Now, if you look at the interpreter in this one, it won't be that helpful to you because it's had everything stripped out of it. It's got very few of the runtime checks left in it. Okay, it only has the type checks left in it. Okay, so this file maybe helps you a little bit, but not that much. It might help you just to see what got removed from it. Okay, but what you really want to do, just show you, is get the language 7 interpreter. Okay, there's the language 7 interpreter. Oops. There's homework 5. Almost everything's the same. The only changes are in evaluate, and evaluate. You know, this one's got all the runtime checks in it. This has almost none of the runtime checks left in it. Okay, the runtime checks are going to be moved by you into here. Okay, so if you look at this one, like here's evaluate in the homework assignment. Here's evaluate if. Here's the evaluate if in language 7. See, there's a runtime check and it's gone. Okay. And now that was the only runtime check in there. Well, oh, no. Here's a runtime check of a type and it needs to stay in there. Okay. So the type checks stay. So the type checks are, if we had more time in the semester, we would learn how to do type checking. That would be like one of the next things to do in this class would be to, maybe we will do that in a little bit of the time that's left, but how could the, we're still leaving the type checking in after the semantic analyzer. Our semantic analyzer is not figuring out types. That would be the next thing to do, is make it sophisticated that it could figure out types. Okay, so right now the type checking is still in there. Okay, but something like, oh, an if statement has to have 3 branches. That's been removed. So this one is going to move into your static analyzer. That one will end up in here under your analyze if. And there might be, so you'll need at least that. Okay, that was a runtime check. That'll need to be at least there. Okay, so you have to see what you do, what code from here moves over here and what code doesn't. Okay, and you get a little bit of a hint by looking at what got removed. This was what language 7 evaluator did, where it's doing all the checking in the evaluator. Here's language 5, which does very little, pretty much only does type checking in the evaluator. That's the only thing that's left. And that would be the next step if we were to go farther into this language, was to figure out how to do the type checking also at analysis time. So your static analyzer at least has to move this guy over to here. Okay. And then you go through and you'll look for other places where there are things in the that were in the evaluator that are no longer in the evaluator that belong in the analyzer. Okay, and read the description. It tries to explain it. This description tries to explain what your analyzer needs to do. Okay, so what we can do is in a week we can come back to this, and if you have questions, then we could maybe at that point you'd have a better sense of what you're trying to do. Okay, so what we want to do today then is go to language 8. Oh, I got language 8 here. I already downloaded it. Whoops. I've already got language 8 down here, and just do some more just studying language 8, because it's from a point of view of modern programming languages. Language 8 really opens the door to a lot of what's going on in Java and JavaScript and C++ and Python. They're going. Language 7 you should think of as C. It's an older style language. Language 8 is a functional language. Okay, and it has these closures that allow you to do some really interesting things. So we want to start looking at some of the interesting things you can do with closures. So it's okay. Now remember, these files up here kind of review the ideas here. So for example, part of what we're working with are these lambda expressions. We're writing functions by themselves without saying what the name of them is. So lambda expressions are a way of saying what a function does without saying it's the f function or it's the squaring function. So like this notation says f takes in x and computes 3x plus 2y, but it doesn't tell you where y comes from, so that's a non-local reference. And that's one of the key ideas, is that between this is not a closed expression. This one's a lambda expression that's not closed. It's got an open variable in it. This one's got a same lambda, same expression, different lambda expression. Now y is the closed variable and x is the free variable. And here's the lambda expression, it's closed. Okay. These would get closed by global variables, some other variable. This one would be closed by a y somewhere else in the program. This would be closed by an x somewhere else in the program. And this one's closed. So this one, when you call it, you give it an x and a y value, and it knows what to do. When you call this one, you give it only a y value. Okay, so that gives you this. The x has got to come from somewhere else. So something has to close off that expression. And that's where the closures come in, is this idea of what is going to close off that lambda expression. Okay, so that's our first idea, is isolating functions as values by themselves. People call them lambda expressions. They call them function values. They also call them function literals. There's lots of different names for them. Function lambda expressions, function values, function literals. Yeah, and not it's different languages use different words. Just whatever. See, I'm trying to think if there's I think there's a four function expression, lambda expressions, function values, function literals. I thought there was a fourth one, maybe some people used. Okay, this is literally a function. See, this is the value you can put in a variable. So, for example, if I want to give that function a name, I might say value g is this. See, then I've given that function a name. Oh, let me show you. In another course, I'm teaching ML, and ML does this. Here, this is the ML programming language, and it does this very beautifully. Like, for example, I write a lambda expression in ML by something like, I write function x, y goes to, say, 3 times x plus 2 times y. Oh, let's see. Oh, I'm sorry. I'm trying. Oh, I now. Yeah, they have the notation's a little bit weird. There's my function, but it takes it. We're going to talk about this in a minute. It takes in x and a y. Notice that I don't write it like this really. See, I'm trying to do this one, but actually, in ML, I write it in kind of a funny way. I say x goes to y goes to 3x plus 2y. So there's a little bit. You don't write xy goes to this. You write x goes to y goes to. This is called currying. Okay, so there's my function. See, it's a function from an integer and an integer to an integer. Okay, but I can't do anything with it because I didn't give it a name. But it's a function value. So I say val g. I want to. This is in ML the way you say give g the value whatever's on the right hand side. So, like I will say val x equal 3, or val s equal cat, because they're values. This is a string value. This is an int value. This is a function value. String value, int value, function value. And I gave that value to g. So now I can say something like g of 4 or 5, or g of 1, 2. Because g, oops, I forgot the semicolon. Okay, see, g is a variable. It's not a function, it's a variable. But the value of that variable is a function. Okay, so we get used to thinking in a different way. In C, you think f is a function. You never think f is a variable whose value is a function. You don't think that way in C. You don't, in Java, you tend not to think that f is a variable whose value is a function. You just think f is a function. X is a int, y is a double, but f is a function. In languages like our language 8 and language like ML, you think that G is a variable whose value is a function. And there's the function value. Over up here, see the function value was that expression there. Okay. And we can do that in our language too, in language 8. We can think this way. Okay. We want to isolate the function value and make that separate from assigning that value to a variable. Okay. This is C-like, there's the variable whose value is this whole kind of thing here. It's very kind of, but notice that there's no equal sign. It's just, this is all one notation. This is all one notation that says that this is the function f1. This is the function f2. This is the function f3. We want it in more modern languages, you separate, you essentially have the name on the left-hand side of an equal sign, like over here, like here. Val s equals cat, s for string. Val x equals 3. You think of the equal sign as giving a variable a value. And then this one, okay. Variable g, value is this function. Okay. And that's a lambda expression. Function literal, function value. Okay. And you think of it just like integers and strings. It's the same syntax. It's actually very purposeful. You use the same syntax for defining string variables, integer variables, function variables. Okay. There's no real difference. G is a variable whose value happens to be a function, as opposed to X is a variable whose value happens to be an integer. Okay. And I can use them, like I can do G of XX. I'm using the variable G is the name of the function, and the variable X is the number, so I can put that number into G 2 times. Okay. So that's one of our first steps, is isolating the notion of a function from the way isolating functions by itself. Isolating functions as things by themselves. Okay. Then once we had functions by themselves, we talked about nested functions. Because remember, there was the free variable idea. Okay. Nested functions are when you put functions inside of some grouping. Okay. So this was, I had that lambda expression. I have x goes to 3x plus 2y. Okay. There's an open lambda expression. Okay. I'm going to nest it in some group, like a block. Okay. In that block, I might say, oh, y is 4. See? This function is nested inside of some block, and it picks up its closure from the block. See, the y is open in this thing. Okay. Now, I've got several ideas going on here. I have to have an open function value. If you don't allow me to have open function values, if this has to be x comma y, then it doesn't matter if it's nested or not. If it's a closed function value, nesting it just doesn't matter because it doesn't pick up anything from its environment. So I want an open function value that is nested. Okay. Now, on the other hand, if I don't nest it at anything, if I just have it like here, that's like C. You could have it non-nested, but then you have to have a global variable. Okay. This would be a global function with a free, this is an open global function, okay? But this isn't the global variable that closes it, okay? Okay. Now this is, okay, remember, now what made this thing down here tricky was the following. Suppose I give this guy a name. Well, actually, here's the way we did it. I created a variable up here. Now I create a variable up here. Then down here, set g equal to that function. But then, whoops. This is where things got tricky. This is why when we have the open function that's nested, that makes reference to this local variable, we have to think hard about what's going on. So if I do something like this, what do I do when I execute g of y? Okay, g is this variable here that's been assigned to this thing. So 5 is the x. Okay, so 5 goes in here. What goes in y? You might say 4, but it's gone. See, when you got to this point, that variable disappeared because it's a local variable. So it's not clear what this means now. We did examples like this. This is what happens when you nest functions, when you nest an open function that's closed by a local variable. So you need to there's no problem if you have a global open function that's closed by a global variable. That's what C does. You can call this you can give this function any name you want, call it anywhere you want. When you call the function, that y will be that y. It's there's no real problem. Essentially, it's just closed right away. It's technically an open function, but in practice, not really. It's just closed by the global variable. That's how C works. Okay, but when you do this, oh yeah, you nest the function inside of something, you close it with a local variable, and and also the function's a first class function. Open first class function value. First class comes from the idea that I can assign it to a variable. So I take that function value and assign it to a variable. So I've got open, nested, first class function. So I've got three things going on. It's open, so it's got a non-local reference. It's first class, because I'm assigning it to something. And it's nested, because it's closed off by a local variable. All those combine together to give me something that I have to think real hard about what it means. Okay, it's not clear what this thing should do. Okay, when you get down here. Okay, if you drop, like here, I drop the nested. Okay, so it just doesn't matter if I give this function a name. It doesn't matter where I call this function. Whenever I call it, doesn't matter where I call it, there's not going to be any problem with what G5 means, because G is closed automatically just by that global variable. Okay. Also, if I give this guy a second parameter, so he's not open, I don't have a problem. This y is immaterial now. So this guy would be called with two parameters, and the fact that I assigned it a value in here doesn't matter. G is that variable, okay? G was created here, so the scope of G is the whole program. G is a global variable. The function value was created locally, but assigned to a global variable. So G is this variable, this value here, but that value just got copied into G, and 5 goes into X, 7 goes into Y, okay? So if I don't have this thing free, there's no problem, even if it is first class and if it is nested. Okay, so if it's not nested, there's no problem. If it's not got a free variable, there's no problem. Okay, if oh, here's another thing that if I call the function here, there's no problem. Okay, there's no problem either. That one, x is 5, y is 4. Yeah. So, yeah, the problem is when I let the first class function escape from the where it's nested. Okay, so that's part of the first class. When I make it first class, it potentially can escape, and it's when it escapes that things really become interesting. So, what really worry is an open first class function value that is nested and escapes. Well, except escaped is not really a term that people, once it's first class, you potentially, this is the function's first class. Here, calling it isn't a problem logically, but here calling it is a logical problem. Okay. This one doesn't seem to cause me any grief, but this one I have to worry about, well, why disappeared on me? So what happens? Okay. The way programming languages solve this problem is that this function carries with it that environment. That's what a closure is. What we really do is, remember a minute ago I said that lambda expressions are our function values. Actually, that's not quite true. A function value is more than a lambda expression. It's the lambda expression and the environment it's nested in that closes it. Okay, so in a sense, in that case, I probably should not call these function values or function literals, or call them function literals, but not call them function values. Say lambda expression is this, but it's not yet a function value. A function value is a lambda expression with the environment that closes it. So I would call this a lambda expression, but G is more than that lambda expression. G is that lambda expression bundled with that environment. That's what we call closure. And that was in our remember we went through this. A value, a lambda tagged value, a lambda value is no longer just code, it's an IP-EP pair. And an IP-EP pair was the tree pointer, which is the code pointer, and the instruction pointer, which is the environment, and the environment pointer. See, it's an instruction pointer and an environment pointer. The instruction pointer points at the lambda expression. What's the code? In this example, G would point at that code. But G will also point, I can't quite draw it, G would point at this block and say, G is that code, and it also carries around that variable. It carries around those two pointers. So that's the lambda expression. So, but then I would say the real function value is the lambda expression bundled with a pointer to that that variable that closes it. Now, when you get here, that environment doesn't actually disappear because there's a reference to it. So it's not garbage collected. So that when you call 5, the y hangs around. So now when you look at these blocks, when you get to the end of a block, you don't think, oh, all the variables go away like I'm taught in C++ and C and Java. You'd say the variables go away if there's no closures inside there. If there's a closure anywhere inside there, a closure would be an open first class function value that's nested. You assign a function value to some variable, that's a closure. And then if that closure escapes, that means this guy doesn't disappear on us. Now, if at some point later on, I say something like set G to be some other lambda expression, okay, now G is a different function value. This function value goes away, and then this block disappears. When I reassign this variable G, that would make this value no longer part of G, but it would also make this block no longer part of G. And then that block, that environment, can finally get garbage collected. So the environment doesn't get garbage collected until it's no longer being referenced by a variable. In this case, a function, a variable that has a function value. Okay. Right. So these are the kind of ideas we've been talking about. And our interpreter, a function value is an IP-EP pair. An IP-EP pair points to code and environment that closes the code. Okay. Now, let's look at how people. Let's look at what programming languages can do with this stuff. Okay. People invented this not just to be obtuse and complicated and convoluted. They created these ideas actually to make in ways that when you get used to them, you can see some very elegant ways that they can be used. Okay, but they're things you've never seen in Java and C++ and C. Yeah, you've never seen these uses of them in language, and that's actually. I mean, some people think that's a real problem with the Java language and C++. That's why Java and C++ are moving more and more towards this more modern style of programming, because there's some things you can do that you couldn't do before. Okay, okay. Here's an example that's real famous. Okay, it's called make adder. Okay, and it's written in language 8. It's a real simple. It's a real short example, but it demonstrates an idea. Okay. Now the language is written in kind of actually. If I run this through the interpreter will print it in a more C-like language, and you might find it a little bit easier to read then. So let me open up a command line here and run the interpreter. Okay, there's a language interpreter, and I'm going to run it with make adder. Okay. Okay, so it ran. So first of all, look at the code in this more pretty printed way. Okay, here's the code in language. Now this code actually looks like Lisp. I mean, this is how you would write it in Lisp pretty much. This is very close to how it'd be written in Lisp. This is how it might look if you, well, actually, this is real close to how it's written in JavaScript. I'll show you in a minute what make adder looks like in JavaScript. It's actually very close to this thing on the left. So I've got a program with a function called make adder. Notice that make adder, what it returns is a lambda expression. So make adder takes in a parameter and gives you back a function from y to x plus y. So it makes an adder function. And what it's saying is that the function it returns, whatever number it gets in, it adds it to this parameter x. Okay. So for example, if I call make adder with 4, so 4 goes into here, 4 is in here, so I have the function that takes in y and adds 4 to y. So I've built the add 4 function. So some people call make adder a function factory. They think of it as something called the factory pattern. Make adder is a factory of functions. Every time you call it, it gives you a new adder function. Like I call make adder 4, it gives me back the add 4 function. Now, so add 4 to 5 would give me back 9. Then if you go down here and look, you see the final answer was 9. Because I called the add 4 function with 5 as the input. Okay. Now, this function in here is an open function. This function in here is one of our open functions. See, it's an open function because it doesn't say where x is. It's nested inside of here, and it's first class because it's being returned to that variable. So I have a nested, open, escaping function. Okay, it's nested, open, and it's first class, and it gets returned to this guy that's outside of his environment. Okay, when I call add 4, somebody has to keep track of x for us. See, because when I call make adder, if you think in terms of C, you create the stack frame for this function, x is 4, you return something, then the function goes away and x goes away. But add 4 is going to carry 2 pointers. It's going to carry a pointer to that code, which is the definition of add 4, but it's also going to carry a reference to that block that holds the x. And if you go down here, you can kind of see that happen. Okay. This is a name in the global environment. So make adder is a name that is a function value. Notice it points to an IP-EP pair. Okay? It points to this function points to that code, and the environment it points to is the global environment. So we can't see inside of it, but this IP-EP pair points to this code and the global environment. Okay, so that's the value of make adder. Make adder is a lambda. Its L value is the IP-EP pair, and I know that that IP-EP pair points to this code and to the global environment. Okay. Now I call make adder. Okay. So here's the call to make adder. This was the assignment of make adder. This was putting make adder in the environment. This is calling make adder. I call make adder with a parameter of 4. That's this parameter here. Okay. When make adder is finished, when make adder returns, it assigns a value to add 4. So that's here. Now add 4 is the return value of having called make adder. So add 4 is a lambda value with another IP-EP pair. Now this IP-EP pair points to that code and this environment here. This is the environment that holds 4. This IP-EP pair points to this environment. This IP-EP pair points to the global environment. This IP-EP pair points to, where is it? This environment here, which holds the 4. Okay. So now add 4 is a lambda tag. It holds an IP-EP pair. Okay. And the IP-EP pair will be a pointer to that code and that environment, which is the environment that was called when you were building that code. See, this was the environment that was from the call to that function. So this guy holds a pointer to the environment that was from the call to this guy. Okay. Now I'm going to call add 4. Okay. When I call add 4, I need to somehow get, okay, now add 4 holds a pointer to this environment here. When I call add 4, I'll pull that environment out, and I'll add to it a new environment that has 5 for y. And that's this guy down here. This is calling add 4. I create an environment that holds a value for y, and it's tied to the EP pair in make adder. Mostly, no, sorry. It's in the EP pair that's in add 4. This is the EP pair that points to that environment. And see this environment here is right there. See, this environment is that environment. That's the environment that add 4 was called in, that make adder was called in. That's the environment that held X. Now that environment is sitting here, it's being used by add 4. Add 4's, this environment did not go away when this function returned. When this function returned, that environment was stored inside add 4. So that when we call add 4, we can restore that environment and tack on to it the y equals 5. And now we can evaluate the lambda expression, because x will go to this x, y will go to that y. Okay, it's tricky. Okay, so and now what is this actually doing? It's allowing you to build what essentially people call function factories. You can build a function that returns functions. Okay, so or another way you can think of it as parameterized functions. Okay, this can be used in all kinds of interesting ways in more sophisticated. This is a baby example, but this gets used a lot. These function factories get used a lot in as a pattern in functional programming. Okay, you give this factory a variable, and it returns to you a function that's specialized to a certain need. Okay, so in this case, we're returning adder functions that add a specific number to their input. Okay, yeah, everybody uses this example as a first example of what you can do with closures. So it's called make adder, and I bet if you just Google it, notice that I Google make adder and I get, can anybody please explain the closure concept or closures in JavaScript? See, you know, if you go to the Mozilla website, where the people, Mozilla are the people who wrote the Firefox browser. This is one of the best places for documentation on JavaScript and HTML. You look up closures, and their first example, or one of their first examples, is make adder. So there's make adder written in JavaScript. It looks a lot like, it doesn't look like our func. Okay. There's make adder in language 8. There's make adder in JavaScript. And there's make adder in our pretty printed language 8. Okay. Our pretty printed language 8 looks a lot like JavaScript. Okay. We have a function called make adder of x. It returns a function. It returns a function that takes in a y. Oh, notice that it returns a function that takes in a y, which returns x plus y. Now I don't need to return. In this language, I don't have the return statement. So the return value of a program is, the return value of a function is whatever is in the body of the function. So in this language, the body of a function is automatically what it returns. Okay, so make adder returns that, and this function returns its body. So the body of make adder is this. The body of that function is this. Every function just returns its body automatically. Okay. In fact, in the newer versions of JavaScript, you don't have to use the return word here. There's a more modern dialect of Java where you don't have to write this return anymore, because a function just returns its body, whatever expression's in its body. So if you rewrite this in a slightly more modern dialect of Java, this return and this return go away. Then they call make adder of 5 is called add 5. Make adder of 10 is add 10. Well, I did uh, add I did make adder of 4 is add 4. Okay. If I wanted, I could duplicate exactly their example here. So and if you go back into the Google of make adder, you'll probably find we'll see JavaScript. I'll bet there's a Python example of it in here too. You can see people call see, I keep seeing stuff about closures. Usually you come across a Python version of it too. If I Google make adder Python, see, it's a homework assignment. Probably in here. There it is. There's make adder in Python. It's actually a question on a homework assignment. Okay. Make adder of n returns the lambda that takes in a k and returns k plus n. Okay. So slightly different syntax, same idea. It's still this guy up here. The Python code still pretty close to our code over here. Not very close to our code over here. This would be the code you'd see if you looked up the make adder in Scheme or Lisp or Clojure. That would look like this. Okay. You can't write make adder in C. You can't write it in Java. Okay. You can't write this function in C or Java or C++. Well, no, you maybe I don't know if you can write it in C++ at this point. Maybe you can write it now in C++. I'm not sure. Okay, but you can't write it in Java and you can't write it in C. Okay, Python can now write it. JavaScript can write it. And a lot of other language, almost any modern language can write it. Okay, I can write it in ML or Haskell. Okay, so now it's a toy example. Make adder is not anybody's idea of a useful piece of code, but it demonstrates this idea of one of the things you can do with closures is create function factories, functions that build other functions for you. Okay. Okay. And it shows that when you call this function that is the function factory and it returns the nested function, what it has to return is a bundle of that function and the environment that held the X. Okay. And that's kind of shown in here. That the value it returns is an IP-EP pair. Okay. Let me see if you can. Yeah, you can't see inside of the IP-EP pair. So the what I haven't been able to figure out a way for you to see inside of them. I mean, I could print right now. They're being printed out in a very a default way where really what this is, it says it's an IP-EP pair at this address. So it's not really telling you at all what's inside of it. And I did that because to print out what's inside of it would just start taking up too much room. And I thought that it was a trade-off between trying to show you what's in the IP-EP pair versus just too much stuff being printed out. So you have to figure out what is in the IP-EP pair. Okay, so the value of add 4, the instruction pointer will be that code. Okay, and the environment pointer was the environment that held the 4, which in this case is that environment there. See, when we called make adder, there was the environment that held the X's 4. So that is the environment that this IP-EP pair is pointing at. add 4, this is the environment in its IP-EP pair. Okay? But you can't see that. I don't know. I can't think of a way to demonstrate that this thing is holding that thing. So that's where you have to understand how this stuff works to know that this guy is holding the reference to this guy here. Now, this guy holds a reference to the global environment. So that we get for free. So if we have a reference to this guy, we also have a reference to the global environment. Okay. Holding a reference to this guy is important because he holds the magic 4 that you need every time you try to call that function. If you call that function without this environment, there's no X. There's no other X in the program. Okay, so when you call this guy here, you're saying what Y is, but you're not saying what X is. So you're expecting this guy to remember what the X is. Okay, and actually, let's go and do like they did in the other example, where they did 2 versions of make adder. Okay, so let's do 2 versions of make adder. Add 6 is apply make adder to 6. Okay, then down here I can apply add 6 to 5. Okay, if I add 4 to 5, I get back 9. If I add 6 to 5, I get back 11. This is calling a function. This is calling add 4. That's the version of this lambda expression that remembers that X is 4. This calls add 6, which is the version of this lambda expression where 6 X is 6. Okay, now if we save this and go over here, okay, now there's a lot more going on because there's, okay, the first few lines are the same. We create the environment that holds make adder. Okay, so we create make adder. Okay, this is calling make adder with 4. Okay, so this is the environment that's stored in add 4. So add 4, this IP-EP pair points to that environment. Okay, this is calling make adder with X equals 6. Okay, this environment is the environment in the add 6 IP-EP pair. So this IP-EP pair is pointing at that environment. So now you can't see it in here, but add 4, it's pointing back at that environment, which holds the 4. And add 6, it's an IP-EP pair. Both of these IP-EP pairs point to the same code. So this IP is that, and this IP is also that. They're pointing to the same code. You know, add 4 and add 6 both point to that code, but they actually have different EPs. This environment, this closure, its EP is that one, and this one's EP is that one. Okay, so one of them is pointing to this environment, which remembers the 6, and one of them is pointing to this environment, which remembers the 4. Okay, now we go to calling add 4 with parameter 5. That's this block here. Okay, we're calling add 4 with its IP-EP pair. Okay, its EP pointed at this block here with the 4 in it. See how when we go to call add 4, there's where 4 reappears for us. Okay, so we go back to that environment, which is chained to the global environment, and then we tack on it another environment which has the binding of, we're calling, we're calling add for with parameter 5. So the parameter 5 is this guy. The closure is this guy. So this is the parameter, this is the closure. The two give us the values we need for x and y. Okay, so that gives the that returns the value of add 4 with 5. Okay. Now what about when you call add 6 with 5? When you call add 6 with 5, that's this chain here. Okay. This IP points to the code. This EP points to, well, it points to this environment way back up here that held the 6. So that's reproduced here. There's the environment that holds the 6. And we chain onto it. We chain onto it the environment that holds the 5. Okay, so there's the binding of 5 to y. There's the closure that holds what the 6 is. There's the y. There's the closure that holds the 6. Okay, so you're calling this, you give it 5 when you call it, and it remembers the 6 in the closure. It gets the 5 in the call. It remembers the 6 from the closure. Okay, it remembers the 6 in the closure. So it's a little bit tricky. Okay? But the key is that we've now used our factory to build two different adder functions. You know, we use our factory to build two different adder functions. The adder functions are actually using the same expression, but they're using different environments. One is using environment holding x4 and one is using environment holding 6. So when we make these calls, we get back different results. Okay, all right. So it's tricky stuff. Most programming languages want to move in this direction, but it's not. It doesn't make programming easier. It makes your code shorter when you've learned how to use this. So in the world where people use this stuff, they can write half the lines of code that a Java or C++ program would write, but half the lines of code, they're more complicated lines of code. Okay, it's kind of taken for granted that it's better to have 1,000 lines of code than 2,000 lines of code. But at the same time, the truth is that the 1,000 lines of code are going to be a little bit trickier. You know, but it's kind of taken for granted that they probably, it seems to be with code, the more lines of code is more important than how tricky the lines of code are. If you have 2,000 lines of code, you're more likely to have twice as many mistakes, even if they are supposedly simpler lines of code. People right now tend to think, and there's evidence that it's right, that number of errors is proportional to the number of lines of code. So if you write 2,000 lines of simple code, you're gonna have twice as many errors as if you write 1,000 lines of kind of complicated code. That might be because the only people who write the slightly complicated code tend to be better programmers. So you end up with errors that are proportional to the number of lines of code. If you give a really novice programmer a complicated language, a functional language, they might end up making more errors in the 1,000 lines of code than they would have made in the 2,000 lines of code of Java. But at least with experienced programmers, they seem to keep getting the result that the number of errors is proportional to the number of lines of code. So if you can come up with a language where you only write 1,000 lines of code instead of 2,000 lines of code to do the same thing, you're probably going to have half the errors. That's kind of the direction people are heading. If the language can let you write fewer lines of code because it's a little bit more abstract like this, you're probably going to end up with fewer errors. But you do pay a price. The lines of code themselves can be harder to read, especially if you're not experienced, if you haven't learned it. Once you've learned it, though, they're not necessarily harder to read. You get used to them. And that's probably the payoff, is that once you've learned and gotten used to the more sophisticated idea, you can then write less code. And if you write less code, you probably have fewer bugs. Okay. And these aren't hard and fast rules yet. Nobody can prove these things. but they've done experiments, and as well as you can experiment with humans writing code, the evidence seems to show that per, errors are proportional to the number of lines of code. 10,000 lines of code will have twice as many errors as 5,000 lines of code. Yeah, there are metrics. Let's see. Errors per lines of code. Okay. Yeah. Like here's a famous metric. 15 to 50 errors per 1,000 lines of delivered code. And it doesn't say what language it's in. Yeah. Ratio of codes per line of code. These people keep, so a lot of times they're reproducing the same, there's not a whole lot of these studies. Okay. But there's a few of them. So there's a lot of people referring to the same studies, but the studies pretty much keep coming up with, the error rate per lines of code doesn't seem to depend on the language. So if a language lets you write fewer lines of code, that makes it better. Okay. They use the KLOC is thousands of lines of code. So they'll talk about errors per KLOC, errors per KLOC, errors per 1,000 lines of code is a pretty good unit. Any sophisticated program is going to be at least 1,000 lines long. And program like 10,000 lines is a smallish project, 50,000 lines is a medium-sized project, 100,000 lines is starting to be a big project. Big projects can be in the millions of lines of code. But when you talk about millions of lines of code, you're talking about like the whole Linux operating system. But no one person writes the whole Linux operating system. It's really a whole bunch of things put together. So I think from a human point of view, you rarely have humans worried about more than a few 100,000 lines of code at a time. You might have a boss who's responsible for a few 100,000 lines of code with his programmers. Probably no one person's responsible for more than 100,000 lines of code. But 1,000 lines of code is kind of a good unit. So defects per KLOC is a common thing. Bugs per line of code. You can see there's, and none of those reference language. Uh, it's not like people say, oh, JavaScript is more buggy than C++. Yeah, that might be true in a small range, but it's not true to any. Yeah, yeah. What's more important is, do you write more lines of code in JavaScript than you write in C? Yeah, if I give you the same problem and I let you write it in JavaScript or in C++, are you going to write more lines of code in JavaScript? And the answer for JavaScript and C++ is probably about no. You'll probably write about the same number of lines of JavaScript as you would C++, unless you understand how to use JavaScript's functional abilities. And if you're really good at using JavaScript's ability to be a functional language, you might be able to write fewer lines of code. But most programmers in JavaScript don't use it functionally. They use it as if it was a version of Java. So they kind of ignore JavaScript's functional ability. So they don't. The make adder. We saw make adder was. We saw it in JavaScript a minute ago. Not many people would even know that JavaScript can do that. When I type this make adder, and the first example was in JavaScript. Right. That's the main documentation page. Not that many JavaScript programmers think this way. They're not even all that familiar with this because they're taught JavaScript as a version of Java and C++, not JavaScript as a version of Haskell or ML, even though JavaScript is a version of Haskell or ML in a certain sense. So this is not most JavaScript programmers' way of thinking. They're not thinking of function factories. Okay. So they're getting to do that more and more often now. They're getting to think a little bit more and more in terms of closures and what they can do for them. Okay. All right. Here's another example that's almost as famous as make adder called make counter. Okay. So here's another example called make counter. Let's look at make counter. make counter. Okay, let's look at. It's a little bit different than make adder. It does something a little bit different. Okay. Oh, let's load it into the interpreter so we can read it in a language that's a little bit more easier to read. Okay. Oh, okay. So let me open a command line. There's the interpreter. Make. What did I say? We're doing make. Counter. Oh, I got a bug. Let's see. I'm missing a parentheses. Okay. Yeah, there's this one's. See, print. I added these prints and forgot to close them. So that needs a closing for the print. I think I added the prints and forgot to close them. So let's see. That I think will fix it. See, yeah, I added the prints and forgot to close them. Okay, let's look at the little bit slightly easier to read. Okay. Make counter takes in a parameter x and returns a void function. It returns a function that takes in no parameters. And then what it does is it adds 1 to x. Okay. So essentially the function is every time you, the return function increments this variable here. So every time you call the return function, it adds 1. So it counts how many times you call it. So make counter, this value is the base of the counter. And then every time you call the return function, it adds 1 to the base of the counter. So here I make counter 4, I get something that counts from 4. Then every time I call count from 4, I get one number larger. So if I call count from 4 once, I'll get 5. If I call it again, I'll get 6. If I call it again, I'll get 7. Okay, because what it's doing is the void function returns its right-hand side. So it actually is returning x plus 1. Okay, so, and this is saying take x, set it equal to x plus 1, itself plus 1, and then return that result. Okay, what's different about this is it's mutating that variable there. Now, if we compare that to the other one, make adder, now what I do? Did I make a change to make adder? Oh, no, yeah. Oh, I'm calling the wrong. I didn't pay attention. I didn't pay attention that I hit tab and forgot that this was the jar file, not the CMD. Okay, now what I do wrong?
Do you have to add the n back to it?
Oh, yeah, I have to add the n back to it. Yeah. Okay. Okay, here's make adder. The other one's make. Make adder, this x just stays whatever you give it. If you give it 4, it stays 4. Notice that nothing changes it. Okay, it's not changing this value. Make counter is weird. It's actually mutating this object that's inside the closure. This mimics object-oriented programming. In fact, this has something to do with the motivation for object-oriented programming decades ago. You can use closures to build objects, because essentially what happens is this X is acting like a private variable inside of an object. And this is acting as a mutator method, a set method. So essentially what I'm doing when I call make counter, I can think of it as make an object that's a counter object. And then I call the add one method in that counter object, and it adds one in my counter object. Okay. And there's actually a huge amount of research or literature out there as closures are a poor man's object and objects are a poor man's closure. That there's this duality between closures and object-oriented programming. Closures and objects are equivalent. Closures as objects. Closures are poor man's objects and objects are poor man's closures. That this example here, this make counter example, shows that you can take a variable and hide it in a closure and then modify it. But only the functions that are part of the closure can modify it. So X is acting like a private variable inside of a closure, inside of an object. And with now, how can I give this object more than one method is a little bit tricky. And there's all kinds of clever ways. See, right now I have an object, but that object only has one method. And objects with only one method aren't really all that useful. So I need a trick to give this object, like what if I wanted to be able to increment it and decrement it? What if I wanted an increment method and a decrement method? Well, I can do that, but it's the code is ugly. Okay, the code is ugly, but it's doable, and it proves that object-oriented programming can be done with closures, and vice versa. You can do closures with object-oriented programming. Okay, but this shows that you can do some interesting things with closure. You can take a language that isn't an object-oriented programming language, but has closures, and emulate object-oriented programming. It's a bit ugly, but people have used it to write compilers and interpreters. People, it's actually considered kind of a good trick by some people. Okay, this idea that I can use a closure to essentially build something like an object that's got private variables. For example, a real famous example is this JavaScript doesn't have private variables. But then somebody realized that JavaScript has closures. So there's a whole style of programming in JavaScript that uses closures to create private variables, which the language doesn't seem to have. But it's an object-oriented programming language. JavaScript's an object-oriented programming language without private variables. All the fields in an object are by default public. But then somebody said, hey, wait a minute. Let's do something weird. Let's use closures to implement it. Let's re-implement objects in JavaScript. So essentially you end up with two systems of object-oriented programming in JavaScript. One using closures that has private variables, and then the one that's not the one that's built into JavaScript, which doesn't have private variables. And there are people doing that kind of thing. If you Google like implementing private variables in JavaScript, probably it'll say in here that you're using closures. No. Yeah, I don't know. Maybe they may just be doing it without pointing out that it's implementing it by using a fancy closure. Okay. This guy's actually the guy who invented this idea. See, Douglas Crockford, he's real famous. He actually is the one who invented this idea that you can sneak private variables into JavaScript. It's usually credited to him. This may actually be the page that he wrote that first described this idea. see 2001. That was a long time ago. That was in early days of JavaScript. He's real famous. He's one of the people who's kind of really done. He's one of the persons who's done the most to help push the JavaScript language forward. So I think this may actually be the page where he first proposed this idea that we can mimic private members in JavaScript by doing a trick with closures. Okay. See, because JavaScript has closures, and he did this at a time when people really didn't even back then. A lot of people had not even noticed that the JavaScript language had closures in it. Yeah, he was one of the first persons to point out that we can really actually make use of the fact that JavaScript's a functional programming language. Okay, so I don't know if he does make adder in this example. Probably make counter. Probably not. Yeah, he doesn't do make counter in this example. But you'll if you scoping and closures, lexical environment examples, explanations, scoping and closures. So make counter and make adder, the two examples that people keep coming back to, the variable scope closure, modern JavaScript tutorial. People keep coming back to these two examples, make adder and make counter. Make adder because it's a good example of a function factory, and make counter because it kind of gets at the idea of you could hide a private variable inside a closure and mutate it. You could mutate the thing that's hidden in the closure. Okay. All right. So we run out of time. There's one more thing. Yeah. Make adder and make counter are two good examples of what people do with closures. Okay. Function factories, mimicking. Yeah, this one's more common. The function factory idea is really common. The let's mimic objects using hidden variables inside of closures kind of gets used by some people, but not a lot. But it's a cute example, but it's not a ubiquitous. It's nowhere near as ubiquitous as this. The third example we want to talk about, we'll do it on Wednesday, is something called currying, which is really common. Something called currying. Well, did I misspell it? Oh, you search for too much. Something called currying. That's another use of closures, and a very important one. JavaScript doesn't do this one. JavaScript, it will see what, but it's part of Haskell and ML, and it's becoming part of well, we'll explain. But this is the third example we'll do of something that people can do with closures that makes them useful in the real world. Okay, function factories, baby objects, and currying are like our three good examples of using closures in the real world to make programming, hopefully make programming, to give you more tools to use to cut down the number of lines of code you have to write. I mean, that's the bottom way. The bottom line is these are supposed to be tricks that give you tools so you can write code in fewer numbers of lines. Yeah. Okay. Currying, closure, function factories. And this one, this one's much less used. Okay. All right. Well, we'll quit there. We're out of time. So we'll do currying on Wednesday. Okay. Oh, and start, if you haven't already, start the homework assignment. And like I say, on Monday, next Monday, if there's any questions on the homework assignment, we can look at the homework assignment and talk about it then. And then I'll also just keep on talking more about the functional programming aspects of language 8. But if anyone's got questions about the programming assignment, we can look at them on next Monday. Okay. All right. So yeah, we'll quit there. If you got questions, write or come to office hours. Okay. Bye-bye. See you Wednesday.